Добрый день, меня зовут Александр Попов.
I'm Alexander Popov from Positive Technologies, and I will be speaking about kernel address sanitizer and hypervisor. Why we need all that? Memory access failures are serious problem for C and C++. Buffer overflow and the use of memory are the vulnerabilities for many attacks, and we certainly wouldn't want to have such vulnerabilities in our C code. Having known that there is a wonderful tool, a wonderful kernel address sanitizing technology, we wanted to have it in our autonomous hypervisor. Here is the structure of my presentation. First of all, I will be speaking about the main principles of the kernel address sanitizer. Then I will be speaking about autonomous hypervisor principles. Then I will be describing the steps and challenges and what we need to do to make SN more stringent and effective. What's a kernel address sanitizer? It's the dynamic memory access controller in Linux. It's an excellent Andrei Konovalov based project. Andrei Konovalov and a group of developers used the user space technology. Kazan was put in the Linux kernel by Andrei Rybinin. 65 memory read failures have been identified with the kernel address sanitizer. It's a debugging tool. When used completely with phasing, it gives an excellent effect. And one of the latest Linux kernel exploits have been found through Kazan plus phasing. Kazan has a very low performance penalty. It slows down the performance only by 1.5 times in comparison with kernel check, which slows down the performance by 10 times. Kazan can be used for B-metal software, and it's nice and it's good, tasty, and we wanted to have it. How it works? The Kazan's main principle is to maintain the information about the controlled memory in the so-called shadow memory. If you have any 8 bytes of the controlled memory in 9 states, you either read and write all of the 8 bytes and the shadow byte says 0, or n first bytes controlled memory from 1 to 7 can be written, others can be not, then n is given to the shadow memory. If all of them are reads only, shadow memory has a negative value in it. How do we control it through Kazan shadow? Here is the schematics which shows the kernel 128 terabytes with k plus 7 bits, and the representation is done like this. Address is divided by 8 and Kazan shadow offset is added here. We have a representation of 8 bytes of virtual space by 1 byte of shadow memory, which makes the code check and verify the shadow. It's the instrumentation at compilation stage. GCC adds the calling of SN load or SN store at each stage. Therefore, GCC adds around global variables and stack buffer the so-called red zone. As soon as the code reads or writes the red zone, the Kazan check immediately signals that something is bad with the memory. I'd like to say a couple of words about hypervisor, an autonomous hypervisor rather. Hypervisor is a software utility which allows you to run a few virtual machines on a host machine. Autonomous B-metal first type hypervisor denotes that this one does not utilize any services of any operating system whatsoever. It's interesting how it utilizes the memory. It has a limited region in the memory with a stack in it, with a heap in it, with the data, with the code of the hypervisor. Sometimes the hypervisor's code reads or writes the memory outward when it interacts with the hardware, which is important to memorize. Now we start some technical details. We put Kasan and V-metal hypervisor. Then we create the pages for shadow memory. Hypervisor occupies 200 megabytes and the shadow memory has 20 megabytes. It's important that we start the address space of the hypervisor in the start of the shadow memory. We have a clear representation of the address space of the hypervisor and the shadow memory. As soon as the hypervisor contacts the shadow memory outside that region, we see that this address is not in the shadow and the hypervisor got somewhere where it was not supposed to, which can be reported. We take a next step in the project, not the entire one, and for one single file we add compilation flags, so the system should allow us to do so, put different flags for different files, and step by step and little by little we add kernel address sanitizer from the Linux file, and we experiment. As soon as with every read and write of the variables in the file, our shadow works well. We see as and store, and we move on forward. We would like to track down the work with the global variables.
Добавляем соответствующий флаг компиляции.
So we add the compilation flag, so JCC. We'll add the required information to the constructor series. So essentially it is analogous to what happens in the Linux core, or the Linux kernel. So upon loading of the hypervisor, these functions will be called, and when that happens, an array of descriptions of the global variables will be transmitted. So that way we will be able to write the poison required into the bytes consistent with the red zones. That way we are actually updating the description in the shadow memory with a negative value, so that we will know that an error has happened when we reach it. However, JCC does not support the instrumentation of the variables declared in the assembler. So, since we want to control access to dynamic memory, we make allocator add red zones to every allocation. Moreover, for every allocation, we will introduce casanlock and casan-free, which will poison red zones, or alternatively, they will fill the whole allocation with the poison consistent with free function. So we have a region in shadow that will be filled with a casan-free poison, which essentially means the memory has been freed. Since allocators like to allocate memory where they've actually just freed it up, to make it more efficient, we should provide for delay allocation so that the poison stays longer in the memory. And we can actually observe stay after free. In a Linux kernel, a shadow will be filled with zeros by default, which means that you can read and write everywhere, which essentially makes it a blacklist. But a perfectionist can never sleep, right? So ideally, we want to poison the whole memory so that no area in the memory is available for read and write. So whenever a section of memory becomes available, we will fill it with zeros. However, when we do stack instrumentation, JCC will work with the shadowing memory on its own. That is, we won't be involved ourselves. Which essentially means that it won't actually fill the shadow memory completely. For example, if the variable is incomplete in the stack, the whole thing will sort of be disrupted. That way, security is compromised. I believe we shall be able to do something about it in the future. So I actually had to put zeros in Kasan init. I actually ran a kind of a competition in my team. Well, after Kasan injection was complete, I wanted to involve my team in implementation of this technology. And I promised a great bounty to all those who could actually perform it. And interestingly, Kasan didn't know anything.
Следующий шаг. Я сказал о том, что нам интересно контролировать, когда наш гипервизор обращается к памяти.
Now, I did say that we want to control for the situations where a hypervisor is trying to address memory, to reach memory outside its region. Now, for that to happen, we need no Kasan API to be on. That way, Kasan will not do any checks in a range of situations. That way, this API can be introduced, and then as we do the grep on source codes, we will be able to find all the areas where the hypervisor is looking outside. However, this API needs to be introduced very carefully, because that way you will, well, effectively nullify the checks. And it will be counterproductive if you do it everywhere. Now the next step actually includes steps 8, 9 and 10, because it's actually very long, because this time we will cover the whole project with our checks. And it's difficult, it's actually painful, because there will be memory access bugs, and the instrumentation will change the time diagram. It will also change the structure of data in the memory, which essentially means that the bugs we didn't see before will now pop up. Which means you need patience for something like this. So an activity like this will require a very thorough code review. Well, our project consists of 55,000 strings of code. This thing took about 3 months, but it was well worth it. So Kasan kernel address sanitizer successfully ported to a bare metal hypervisor. And interestingly, Kasan was able to find some mistakes, some bugs that were not really discovered by 3 code auditors. Moreover, we're happy to discover poison by default and the ability to look for instances where functions look outside their region in the memory. Shown here is my patch to the Linux kernel. Interestingly, Kasan itself is a great technology that can help you in the software development process. So while you're still in the context, while you're still doing the code, it actually shows all the mistakes you make, which is great. Thank you very much. I can take your questions now. Do we have any questions?
Да, спасибо.
Well, I think that you can ask questions later.